You notice it first, not as a direction, but as an absence. There is no moment in your life, or in any life that has ever been lived on this planet, or in the entire recorded history of anything humans have bothered to measure, where something was perfectly still. The rock on the shelf is vibrating at the atomic level, its lattice of silicon and oxygen trembling in place at frequencies your hand will never detect. The air in the room is a continuous riot of nitrogen and oxygen molecules bouncing off each other at hundreds of meters per second, individually invisible, collectively the thing keeping you alive. The Earth is spinning. The solar system is orbiting the galactic center. The galaxy itself is moving toward something called the Great Attractor, a gravitational anomaly so large it pulls hundreds of galaxies in its direction, and even that structure is embedded in a larger flow, and that flow in a larger one still. Nothing has ever stopped. This is not a poetic observation. It is a precise one. The universe, from the moment of its beginning, has been in a state of motion that has never once reversed into stillness. Not local stillness. You can cool a small object close to absolute zero and watch its motion reduce to something almost theoretical, but total, universal, background stillness. That has never existed. Not for a single Planck time. Not for the smallest unit of duration the laws of physics are capable of describing. What this chapter asks you to sit with is not the fact of that motion, but the direction of it. Because there is a direction. Not in the way that wind has a direction. Not pointing somewhere specific the way a compass needle points north. The direction is subtler and stranger and more total than that. It is written into the structure of matter itself, into the way particles behave when they interact, into the way time moves through a system and leaves things different than it found them. The universe has a current. You are in it right now. Everything you have ever touched has been in it. Every atom that has ever existed in the observable universe has been carried by it. The mystery is not that the current exists. The mystery is that it exists at all. Because according to the most fundamental equations physicists have written to describe reality, the equations that govern how particles behave, how forces operate, how matter and energy interact at the deepest level anyone has yet been able to probe, the universe should not have a preferred direction. The mathematics is almost perfectly symmetric. If you ran the laws of physics backward, most of them would look the same. If you replaced every particle with its antiparticle counterpart, most of the equations wouldn't flinch. The universe that the equations describe is very nearly a universe without a preference. And yet here we are. Here everything is, moving in one direction, composed of matter and not antimatter, persisting when it should, by the mathematics, have annihilated itself completely in the first second of its existence, and left behind nothing but light. This chapter doesn't explain why. It can't, and neither can anyone, not completely, not yet. But it asks you to feel the weight of the question before the attempted answers begin arriving. Because the question is older than any answer that has been proposed for it, and it will likely outlast most of them. And there is something right about starting there, in the motion itself, in the current, in the sensation of being carried by something so large and so old that naming it barely helps. The universe is flowing in one direction. It has been doing this for longer than the word long has any meaning, and we are only beginning to understand why. Before the universe had objects, it had tendencies. This is not a mystical claim, it is a structural one. The laws of physics, the actual rules governing how particles interact, how forces manifest, how energy distributes itself, are not neutral. They are not a blank surface on which events happen to occur. They are themselves shaped, angled, leaning in ways that took decades of experimental physics to even detect, and whose full implications are still being worked out in laboratories and on blackboards and in the quiet of theoretical physicists' offices at 2 a.m. The technical language for what this chapter is about is CP violation. C stands for charge conjugation, the transformation that turns every particle into its antiparticle, swapping positive charge for negative and vice versa. P stands for parity, the transformation that flips space, replacing every left-handed process with a right-handed one, as though the universe had been reflected in a mirror. For most of the 20th century, physicists assumed that the combined symmetry of these two transformations, CP, was a genuine symmetry of nature. That if you took any physical process, replaced all particles with antiparticles, and also reflected the spatial coordinates, the resulting process would be indistinguishable from the original. It isn't. But this chapter is less interested in what CP violation is than in what it means to live inside a universe that has it. To understand that, it helps to think about what a truly symmetric universe would feel like. Imagine a universe in which every physical process and its mirror image and its charge-reversed counterpart were equally probable. A universe in which there was no sense, at any level, in which any configuration of matter or energy was preferred over any other. Such a universe would be, in the deepest possible sense, impartial. It would have no angle, no lean. Given time and interaction, any asymmetry that arose would be exactly balanced by an equal and opposite asymmetry somewhere else. The universe would average itself out. It would tend toward a kind of deep equilibrium in which no particular arrangement of matter was any more stable or probable than any other. That universe would be empty. Not empty in the sense of having no energy. It might be full of energy. But it would be empty of structure, empty of matter. Because in such a universe, the matter and antimatter produced in the first moments of existence would have annihilated each other with perfect efficiency, leaving behind only photons, only light, propagating through a universe of pure radiation with no galaxies, no stars, no planets, no chemistry, no anything that organizes itself into complexity. The universe we actually inhabit is different because somewhere very early in its history, at energies so extreme that no accelerator humans have ever built comes close to reaching them, the rules were not balanced. The symmetry cracked. Or rather, the symmetry was never quite there to begin with, only assumed. And when the asymmetry became visible, when experiments eventually showed that certain particles did not behave identically to their antiparticle counterparts, the implications were enormous. The word preference is not used here casually. The universe did not choose. It has no agency. But the laws it operates under are not indifferent to configuration the way a perfectly fair coin is indifferent to which face it lands on. They are slightly, measurably, consequentially biased, and that bias, that weight on one side of the scale, is the reason you exist to read this. The history of how physicists came to understand this is inseparable from the history of a particular symmetry they were convinced nature had to obey. The symmetry wasn't invented as a convenience. It emerged from the mathematics of quantum field theory as something that seemed mandatory. When you write down the equations that govern how fermions, matter particles with half-integer spin, interact with force-carrying bosons, the equations appear to demand certain symmetries. The universe described by those equations looks the same if you reflect it, looks the same if you swap particles for antiparticles, looks the same if you do both at once. The experimental discovery that this was wrong did not arrive cleanly. It arrived in pieces. Each piece initially resisted, debated, reinterpreted, and only slowly accepted as evidence of something genuinely new in the structure of nature. The first piece was parity violation, and it arrived in the late 1950s with such force that it restructured fundamental physics almost overnight. But parity violation alone, the discovery that the universe distinguishes left from right, was not enough to explain the matter-antimatter asymmetry. A left-handed universe and a right-handed universe, if they are exact mirror images of each other with particles and antiparticles swapped appropriately, can still be globally symmetric. The asymmetry required something more. That something more is CP violation, the discovery that even the combined transformation, reflecting the universe and swapping all charges, does not produce an identical process. There are physical processes in nature that know the difference between a particle and its antiparticle even after reflection. They proceed at different rates. They have, in the most technical and precise sense available, a preference. The particles where this preference was first clearly observed are called kaons, K-mesons, composite particles made of one quark and one antiquark, unstable, short-lived, and sensitive to violations of symmetry in ways that make them extraordinarily useful as probes of the universe's asymmetric tendencies. The 1964 experiment by Cronin and Fitch that demonstrated CP violation in kaon decay won a Nobel Prize 15 years later, which gives some sense of how long it took the physics community to fully absorb what had been shown. What had been shown was this: the universe is not symmetric between matter and antimatter, not perfectly, not even approximately. It has a weight to it, a lean, a preference so subtle that it took decades to detect and is still not fully understood, but so consequential that without it, nothing would exist. This chapter is not the place to trace all the mechanisms through which that preference operates. Those come later, in greater detail. But the weight of the preference needs to be felt before the mechanisms can mean anything. The universe is not a balanced scale. It is a slightly unbalanced one, and everything that has ever existed is sitting on the heavier side. There is something almost vertiginous about this if you let it settle. The matter you are made of, not just you personally, but all matter, all the atoms in all the stars in all the galaxies of the observable universe, is the residue of an imbalance, a cosmic tipping. The universe weighed itself in the first fraction of a second, and came up fractionally heavier on one side, and what fell off the lighter side was annihilated, and what remained on the heavier side became everything. That small lean is the whole story. Every subsequent chapter is an attempt to understand where the lean came from. There is a laboratory in Washington, D.C. in the winter of 1956, and in it a cobalt-60 source is being cooled to a temperature near absolute zero. The physicist overseeing the experiment is Chien-Shiung Wu. She has spent months on this setup. The cobalt nuclei, once cooled sufficiently, will align their spins along a magnetic field, and Wu wants to watch which direction the electrons emitted in beta decay fly off, relative to that alignment. The question behind the experiment is precise. Does the weak nuclear force, the force responsible for beta decay, behave identically in its mirror image? The question had seemed almost unnecessary to ask. Parity symmetry was considered so fundamental that suggesting it might be violated was, in the words of one physicist at the time, like suggesting that God was left-handed. But two theorists, Tsungdao Li and Chenning Yang, had gone through the existing experimental literature and found something alarming. Parity conservation in the weak interaction had never actually been tested. It had been assumed. Wu's experiment tested it. The electrons were not emitted symmetrically. They had a preferred direction. The weak force, it turned out, was not symmetric under spatial reflection. The universe knew the difference between left and right. The news moved through the physics community with unusual speed. A party was reportedly interrupted when a phone call arrived with the preliminary results. Wolfgang Pauli, who had declared that he did not believe God was a weak left-hander, had to be informed that he was wrong. Li and Yang received the Nobel Prize in Physics in 1957, the same year as the experiment, an almost unheard-of speed for a Nobel committee. But this chapter is not really about that party, or about the Nobel, or even about the historical drama of parity's fall. It is about what happens in the mind when a symmetry you believed in is removed. Because parity wasn't just a technical assumption, it was a deeply intuitive one. The laws of physics should look the same in a mirror. Why wouldn't they? What possible reason could the universe have for caring about handedness at a fundamental level? There's no external reference frame that makes left different from right in any absolute sense. The distinction is relational, not intrinsic, and yet the weak force cares. Deeply. The W boson, which carries the weak interaction, couples exclusively to left-handed particles and right-handed antiparticles, not preferentially, exclusively. There is no weak interaction for right-handed electrons in the standard model. The mirror universe, the one where all spatial coordinates are reflected, would be governed by different physics than ours. The discovery of parity violation opened a question immediately. Was this a violation of P alone, or was it part of a larger pattern? If you reflected the universe and also swapped every particle for its antiparticle, would the physics then be symmetric? This combined transformation, CP, seemed to many physicists like it had to be preserved even if P alone was not. The mathematics of quantum field theory, interpreted in certain ways, seemed to require it. Then, 8 years later, CP fell too. The 1964 Cronin-Fitch experiment observed that neutral kaons, particles that quantum mechanically mix with their own antiparticles, did not decay with the equal probabilities that perfect CP symmetry would demand. The violation was small, measured in parts per thousand, but it was real, it was reproducible, and it meant that the universe was not even symmetric under the combined transformation of charge conjugation and parity. The room where CP symmetry broke was quieter than the one where P had broken. The result was more technical, more difficult to interpret, but the implication was, in some ways, more profound. The universe genuinely distinguishes between matter and antimatter. not just in the way it handles spatial orientation, but in the dynamics of how certain particles decay. The arrow of preference goes all the way down into the interactions themselves. What this chapter wants to hold is not the experimental timeline, but the phenomenology of the broken mirror. Try to hold in your mind the image of a universe in which the mirror is still intact, in which every process and its reflection and its charge-reversed counterpart are indistinguishable. It is a cleaner universe in a certain aesthetic sense, more symmetric, more mathematically elegant, the kind of universe that might feel like it was designed. The universe we actually have is messier. It has a handedness. It has a charge preference. The cobalt nuclei aligned in Wu's cold laboratory were already carrying, without knowing it, the signature of that messiness. The fact that the weak force they were subject to was not neutral, was not balanced, was leaning already in the direction of the universe's fundamental preference for matter over antimatter. The crack in the mirror is still visible if you know where to look, and everything on this side of it, every atom of everything, is the result. There is a fraction that this chapter needs you to try to hold. Not to understand it quantitatively, that is probably not possible, and the attempt isn't the point, but to feel its scale, to sit with its smallness long enough that it starts to produce something other than incomprehension. The fraction is approximately 1 part in 10 billion. Written numerically 0.0000000001, or 10 to the power of -10 in scientific notation, which is cleaner but perhaps too clean. It domesticates the number in a way that lets you look at it without really feeling it. This is the estimated ratio of the matter excess in the early universe. For every 10 billion antiprotons in the first moments after the Big Bang, there were 10 billion and 1 protons. For every 10 billion antineutrons, 10 billion and 1 neutrons. The matter and antimatter were very nearly equal. Not exactly equal, that 1 in 10 billion excess is why we are here, but close enough that the difference, expressed as a fraction, is essentially invisible. Here is what happened to the other 10 billion. They annihilated each other. Proton met antiproton. Neutron met antineutron. Electron met positron. Matter and antimatter collided in the dense, hot plasma of the early universe and converted each other entirely into photons, into light. The annihilation was almost perfectly complete, almost perfectly mutual, almost. The survivors, the 1 in 10 billion excess, had no antiparticle partner to annihilate with. They simply remained. As the universe cooled, as quarks bound into protons and neutrons, as protons and neutrons assembled into nuclei, as nuclei captured electrons into atoms, the survivors became everything. Every atom in every star, in every galaxy of the observable universe traces its existence to that 1 in 10 billion surplus. The number requires sitting with before it can mean anything. Consider 10 billion grains of sand. If you've ever stood on a beach, you've stood near the vicinity of this quantity, though a beach of significant size has substantially more. 10 billion grains, spread across a surface large enough to hold them, would cover a substantial fraction of a sports field. Now imagine that you add a single grain to that field, 1 grain, and then imagine that, through some process, every grain on the field finds a partner grain and the two of them vanish together, annihilating each other, removing themselves from existence. At the end of the process, all you have is that 1 extra grain. That 1 grain is everything. The numbers involved in the actual event are, of course, far larger than any physical analogy can contain. The early universe contained not 10 billion particles, but something closer to 10 to the power of 88 particles, a number that has no intuitive analogue in human experience. But the ratio is the same. For every 10 to the power of 88 antiparticles, there were 10 to the power of 88 plus something very small particles. The something very small survived. The rest became the cosmic microwave background, the faint glow of radiation that still permeates the universe, and that we can detect today with our instruments, the residual warmth of the annihilation of nearly everything. This is what makes baryogenesis, the process by which the matter excess was generated, so extraordinarily difficult to explain. The excess is so small that explaining it requires a mechanism precise enough to produce, from an initially symmetric state, a deviation of 1 part in 10 billion. Not more, not less. Exactly enough to leave behind the baryon density we observe today. The word baryon is the technical term for particles made of 3 quarks, protons and neutrons, the heavy particles that make up atomic nuclei. Baryogenesis refers to the generation of the observed baryon symmetry. It is one of the central unsolved problems in physics. And it is unsolved not for lack of candidates. There are several proposed mechanisms, but because none of the candidates fully accounts for the size of the asymmetry we observe. The Standard Model, the theoretical framework that describes the behavior of all known particles and forces, does contain CP violation. But the amount of CP violation it contains is not enough, not even close to enough. The asymmetry the Standard Model can generate from its existing CP-violating processes is many orders of magnitude smaller than the 1 in 10 billion ratio we need to explain. This is one of the cleanest signals in physics that there is something beyond the Standard Model, something missing, some process, some particle, some interaction that has not yet been discovered that contributed the missing symmetry. The Standard Model is extraordinarily successful as a description of particle physics. It has predicted experimental results with a precision that remains extraordinary even after decades of testing. But it cannot explain why you exist. That is not a rhetorical flourish. It is a precise statement. The Standard Model, taken alone, cannot generate a baryon asymmetry large enough to produce the universe we observe. Something else happened. What else happened is not fully known. But we can describe the space of possibilities with some precision, thanks to a set of conditions worked out in 1967 by a physicist named Andrei Sakharov, whose 3 conditions for baryogenesis define the problem more clearly than any other single contribution in the field. Those conditions come in the next chapter. But this chapter asks for something first, a recognition of scale. The mystery of matter's survival is not a mystery at the scale of daily life. You do not feel it. The atoms around you do not whisper of their improbability. The coffee cup does not seem like a survivor. But it is. Everything material is a survivor of an annihilation so complete that the survivors constitute 1/10 billionth of the original population. The rest is light. The rest is the photons of the cosmic microwave background, the ancient thermal glow of a near-total mutual destruction, still cooling, still spreading, 13.8 billion years later. There is a certain kind of vertigo available in this fact if you allow yourself to feel it. Not the theatrical vertigo of science communication, the breathless wonder of it all vertigo, something quieter, something more like the feeling you get when you realize that what you took to be the normal background of existence is actually an extremely unlikely residue of something catastrophic. The universe is mostly photons. Matter is the exception. You are the exception. The number that describes how much of an exception you are is 10 to the power of minus 10. Sit with that for a moment before moving on. In 1967, Andrei Sakharov was not primarily a cosmologist. He was a theoretical physicist who had helped design the Soviet hydrogen bomb and who was beginning, carefully and at personal risk, to speak publicly about nuclear weapons and human rights. The paper he published that year in a Soviet physics journal was 4 pages long. It addressed a problem most physicists were not yet thinking about: why the universe contains more matter than antimatter, and it proposed 3 conditions that any successful mechanism for generating this asymmetry would have to satisfy. The paper was largely ignored for several years. It was rediscovered in the 1970s when the problem of baryogenesis began attracting broader attention, and by the time its importance was fully understood, it had become one of the most cited papers in the history of cosmology. The 3 conditions are now known simply as the Sakharov conditions, and they define not a solution but the shape that any solution must take. Understanding them requires following a particular kind of logic, not the logic of deduction from first principles, but the logic of constraint. Sakharov was not saying, "Here is how the asymmetry was generated." He was saying, whatever generated it, the mechanism must have had these 3 properties. If any of them was absent, no asymmetry could have been produced. All 3 are necessary. None is sufficient alone. They are a set of locked doors, and the solution to baryogenesis must pass through all of them. The first condition, baryon number violation. This one is the most immediately logical, but also the most radical. Baryon number is a quantity assigned to particles. Protons and neutrons each have a baryon number of +1. Their antiparticles have a baryon number of -1, and most other particles have a baryon number of 0. In ordinary physics, the physics we can observe in laboratories, the physics that governs everything from nuclear reactions to particle collisions in our most powerful accelerators, the total baryon number is conserved. You cannot create more protons than antiprotons, or destroy protons without destroying an equal number of antiprotons. The books balance. But if the books always balanced, the universe would always have had equal numbers of baryons and antibaryons. If it started with 0 net baryon number, which is the most natural assumption, since a universe that began with a net baryon number already built in would simply be pushing the asymmetry problem back to initial conditions, then any process that conserves baryon number will never generate an asymmetry. To get more baryons than antibaryons, you need a process that can create baryons without creating an equal number of antibaryons, or destroy antibaryons without destroying an equal number of baryons. Baryon number, in other words, must be violated. This is a significant claim. There is no confirmed observation of baryon number violation. Protons, as far as experiment has shown, are stable, or if they decay, they do so with a lifetime so long that it exceeds the current experimental sensitivity of very large detectors that have been watching and waiting for decades. The Standard Model does contain a mechanism for baryon number violation, called Sphaleron processes, which become important at very high temperatures, the temperatures of the early universe. But whether and how this mechanism contributed to baryogenesis remains an open question. Many extensions of the Standard Model predict baryon number violation at detectable rates. So far, none has been detected, but the theoretical argument is clean. Without baryon number violation, no asymmetry is possible. The second condition, C and CP violation. This condition connects back to the previous chapters. Even if baryon number violating processes exist, they must proceed at different rates for particles and antiparticles. If a process creates baryons and the exactly CP conjugate process creates antibaryons at the same rate, the asymmetry still doesn't accumulate. The two processes cancel each other out. This is where the experimental evidence for CP violation becomes directly relevant to baryogenesis. The universe's preference for matter over antimatter can only have been generated if, somewhere in the chain of early universe processes, matter and antimatter were treated differently. The CP violation observed in Kaon and B-meson decays shows that such differential treatment is possible in principle. But, and this is the critical point, the amount of CP violation currently known in the Standard Model is not sufficient to generate the observed asymmetry. The preference it encodes is too small, too subtle. This means either that there are additional sources of CP violation not yet discovered, new particles, new interactions, new mechanisms that haven't yet appeared in accelerator experiments, or that the mechanism of baryogenesis operated through pathways very different from the ones currently best understood. Either possibility points beyond the current framework of physics to something new. The third condition, departure from thermal equilibrium. This is the subtlest of the three conditions, and in some ways the most surprising. Even if baryon number violating processes exist, and even if they treat matter and antimatter differently, there is still one more thing required. The processes must occur out of equilibrium. Here is why. In a system in perfect thermal equilibrium, every process and its reverse occur at exactly equal rates. The forward reaction and the backward reaction balance. This is a direct consequence of what physicists call the CPT theorem, the principle that physics is symmetric under the combined transformation of charge conjugation, parity reversal, and time reversal together. This symmetry is believed to be exact, a fundamental property of any relativistic quantum field theory. And it implies that in equilibrium, where time reversal symmetry effectively holds at the statistical level, any CP violating process that creates a baryon excess will be exactly balanced by its reverse process destroying an equal baryon excess, and the solution to baryogenesis must pass through all of them. The first condition, baryon number violation. This one is the most immediately logical, but also the most radical. Baryon number is a quantity assigned to particles. Protons and neutrons each have a baryon number of +1. Their antiparticles have a baryon number of -1, and most other particles have a baryon number of 0. In ordinary physics, the physics we can observe in laboratories, the physics that governs everything from nuclear reactions to particle collisions in our most powerful accelerators, the total baryon number is conserved. You cannot create more protons than antiprotons, or destroy protons without destroying an equal number of antiprotons. The books balance. But if the books always balanced, the universe would always have had equal numbers of baryons and antibaryons. if it started with zero net baryon number, which is the most natural assumption, since a universe that began with a net baryon number already built in would simply be pushing the asymmetry problem back to initial conditions, then any process that conserves baryon number will never generate an asymmetry. To get more baryons than antibaryons, you need a process that can create baryons without creating an equal number of antibaryons, or destroy antibaryons without destroying an equal number of baryons. Baryon number, in other words, must be violated. This is a significant claim. There is no confirmed observation of baryon number violation. Protons, as far as experiment has shown, are stable, or if they decay, they do so with a lifetime so long that it exceeds the current experimental sensitivity of very large detectors that have been watching and waiting for decades. The Standard Model does contain a mechanism for baryon number violation, called sphaleron processes, which become important at very high temperatures, the temperatures of the early universe. But whether and how this mechanism contributed to baryogenesis remains an open question. Many extensions of the Standard Model predict baryon number violation at detectable rates. So far, none has been detected, but the theoretical argument is clean. Without baryon number violation, no asymmetry is possible. The second condition, C and CP violation. This condition connects back to the previous chapters. Even if baryon number violating processes exist, they must proceed at different rates for particles and antiparticles. If a process creates baryons and the exactly CP conjugate process creates antibaryons at the same rate, the asymmetry still doesn't accumulate. The two processes cancel each other out. This is where the experimental evidence for CP violation becomes directly relevant to baryogenesis. The universe's preference for matter over antimatter can only have been generated if, somewhere in the chain of early universe processes, matter and antimatter were treated differently. The CP violation observed in Kahn and B-meson decays shows that such differential treatment is possible in principle. But, and this is the critical point, the amount of CP violation currently known in the Standard Model is not sufficient to generate the observed asymmetry. The preference it encodes is too small, too subtle. This means either that there are additional sources of CP violation not yet discovered, new particles, new interactions, new mechanisms that haven't yet appeared in accelerator experiments, or that the mechanism of baryogenesis operated through pathways very different from the ones currently best understood. Either possibility points beyond the current framework of physics to something new. The third condition, departure from thermal equilibrium. This is the subtlest of the three conditions, and in some ways the most surprising. Even if baryon number violating processes exist, and even if they treat matter and antimatter differently, there is still one more thing required. The processes must occur out of equilibrium. Here is why. In a system in perfect thermal equilibrium, every process and its reverse occur at exactly equal rates. The forward reaction and the backward reaction balance. This is a direct consequence of what physicists call the CPT theorem, the principle that physics is symmetric under the combined transformation of charge conjugation, parity reversal, and time reversal together. This symmetry is believed to be exact, a fundamental property of any relativistic quantum field theory. And it implies that in equilibrium, where time reversal symmetry effectively holds at the statistical level, any CP violating process that creates a baryon excess will be exactly balanced by its reverse process destroying an equal baryon excess. Under a mountain in northern Minnesota, 716 meters below the surface, there is a tank. The tank holds 8,000 metric tons of water. It is lined with 4,700 photomultiplier tubes, light detectors of extraordinary sensitivity, capable of registering the faint flash produced when a charged particle moves through the water faster than light travels through that medium. The whole apparatus is underground because rock is an effective shield against the cosmic ray muons that would otherwise trigger false signals constantly, saturating the detectors with noise. This experiment, and others like it in other countries, Super Kamiokande under Mount Aquino in Japan is the most famous, are watching for something that has never been seen. They are watching for a proton to decay. The proton is, as far as ordinary experience suggests, perfectly stable. The proton at the center of the hydrogen atom in the water molecule in the glass on your desk has been there since that hydrogen atom formed, which was possibly within the first few 100,000 years after the Big Bang. It has not decayed. The proton at the center of your body's hydrogen atoms has been there since before the Earth formed, still not decayed. There is no confirmed observation of proton decay anywhere in the history of experimental physics, and yet the first Sakharov condition, baryon number violation, requires that proton decay, or something like it, must be possible. If baryon number is a perfect conservation law, no mechanism can ever change the total number of baryons in the universe. But if proton decay is possible, then baryon number is not conserved. Protons can, in principle, transform into other particles, releasing their baryon number in the process. Many of the theoretical frameworks proposed as extensions of the Standard Model, Grand Unified Theories, or GUTs, predict that protons should decay. The predictions vary in the predicted lifetime and in the decay products, but the general claim is consistent. Protons are not truly stable, only extremely long-lived. The predicted lifetimes in various GUT models range from around 10 to the power of 34 years to 10 to the power of 36 years and beyond. To understand what this means, consider that the current age of the universe is approximately 1.38 times 10 to the 10th power years. The proton lifetime predicted by the simplest GUT models is 10 to the 34th power years, roughly 1 trillion times the current age of the universe. If you had a box of protons and waited that long, perhaps half of them would have decayed. But you don't have to wait that long. You can do something more clever. If you have enough protons in one place, and if you watch all of them simultaneously, the statistics work in your favor. A tank of 8,000 tons of water contains approximately 5 times 10 to the power of 33 protons. If the proton lifetime is 10 to the power of 34 years, you would statistically expect to see about 1 decay every 2 years, somewhere in that tank. The photomultiplier tubes would detect it. The Cherenkov light flash of the decay products moving through the water, a brief distinctive signature in the dark. Super Kamiokande has been running since 1996. Its predecessor Kamiokande was running before that. The searches have been going on for decades. No proton decay has been seen. This has ruled out the simplest GUT models, those predicting the shortest proton lifetimes, and pushed the experimental lower limit on the proton lifetime to above 10 to the 34th power years for the most commonly predicted decay channels. This does not mean proton decay doesn't happen. It means that if it happens more slowly than the ruled-out models predicted. The more complex GUT models and supersymmetric extensions of the standard model predict longer proton lifetimes that remain experimentally untested. The search continues. There is something peculiar about this kind of experiment, not in a critical way, but phenomenologically. Most physics experiments are active. You fire a beam at a target, or you collide two particle streams, or you apply a field to a material and measure the response. Something is being done. In proton decay searches, nothing is being done except watching. The protons are just there, sitting in their tank of cold water under a mountain, and the detectors are watching for one of them to, spontaneously and without external provocation, cease to be a proton. The watching has been continuous for decades. Shifts of physicists monitoring the detector outputs, automated trigger systems flagging candidate events for human review, careful work distinguishing the signatures of atmospheric neutrino interactions, which do happen constantly in the tank, neutrinos being far more abundant and interactive than proton decay events would be, from the signal of an actual proton dying. Nothing yet. The absence of a signal is itself a result. Every year the search continues without a detection. The lower limit on the proton lifetime rises. The constraints on theories tighten. The simple models are eliminated one by one. What remains are theories that push the proton's lifetime ever further into the unmeasurable future, or theories that predict decay through channels so rare or so difficult to detect that current experiments cannot reach them. There is a version of the story in which proton decay is eventually observed. In the next generation of detectors, currently planned and in some cases already under construction. Hyper-Kamiokande with 260,000 tons of water is designed to push the search further. Dune, the deep underground neutrino experiment in South Dakota, is being built with proton decay sensitivity as one of its primary goals. And there is another version in which the proton is genuinely, permanently stable, in which baryon number violation, while required by the logic of baryogenesis, proceeded through a mechanism that doesn't leave any trace detectable today, or operated only at energies so extreme that no echo of it survives at the energies accessible to experiment. Both versions are currently consistent with what we know. The tank under the mountain continues to wait. The photomultiplier tubes continue to watch. And the protons continue to hold themselves together, stable beyond any clock we possess to measure the word stable against. Consider water freezing, not ice forming in a freezer, which happens quickly and in a context you understand. Consider instead perfectly pure water, cooling slowly in perfectly still conditions, passing through 0 degrees Celsius and continuing to drop without crystallizing, remaining liquid below its nominal freezing point through the phenomenon of supercooling, until something, some microscopic irregularity, triggers nucleation, and in that moment the entire system reorganizes. The structure that was latent in the water, encoded in the shape of the hydrogen bond, in the geometry of the oxygen atom's electron configuration, becomes actual. The liquid phase gives way to the solid phase, and the ice crystal that forms reflects the underlying symmetry of the water molecule in a pattern that persists indefinitely as long as the temperature stays below freezing. This transition has a name in physics, a phase transition. And phase transitions are important to the story of baryogenesis because the early universe underwent several of them as it cooled from its initial extreme temperature, and those transitions are among the leading candidates for the non-equilibrium environments that Sakharov's third condition requires. The most relevant of these for the purposes of the matter-antimatter asymmetry is the electroweak phase transition. To understand this transition, it helps to understand what was happening before it. In the very early universe, at temperatures above approximately 10 to the power of 15 degrees Kelvin, a temperature so extreme that no meaningful analogy to ordinary thermal experience is possible, the electromagnetic force and the weak nuclear force were unified into a single electroweak force. The distinction between them that we know from everyday physics, the electromagnetic force governing light and charge, the weak force governing radioactive decay, did not exist. They were aspects of a single interaction carried by particles that were, at those temperatures, all effectively massless. Then the universe cooled below the electroweak transition temperature, and something changed. The Higgs field, which permeates all of space, and with which all massive particles interact, underwent a transition analogous to the freezing of water. Above the transition temperature, the Higgs field was in a symmetric state, a state of high symmetry in which the W and Z bosons, which carry the weak force, had no mass. Below the transition temperature, the Higgs field settled into a new configuration, a lower energy state with less symmetry, and in doing so it gave mass to the W and Z bosons. The electroweak symmetry was spontaneously broken. The unified electroweak force separated into the electromagnetic force and the weak force as we know them. The transition itself is what interests us here. Whether this transition was continuous and smooth, what physicists call a second order or crossover transition, or abrupt and discontinuous, a first order transition involving bubbles and latent heat, analogous more to boiling than to gradual cooling, determines whether it could have generated the baryon asymmetry we observe. In the standard model of particle physics, the electroweak transition is a smooth crossover, not a first-order phase transition. The Higgs mass, now measured to be approximately 125 gigaelectron-volts, is too large for a first-order transition in the standard model, and a smooth crossover does not provide the dramatic departure from equilibrium that Sakharov's third condition requires. It proceeds too gently. The baryon number-violating Sphaleron processes, which are active at high temperatures and are suppressed at low temperatures by the Higgs mechanism, simply turn off gradually as the universe cools, without any opportunity for an asymmetry to be generated and locked in. This means that if baryogenesis occurred at the electroweak scale, at the temperature of the electroweak transition, it requires physics beyond the standard model. Extensions of the standard model that modify the properties of the Higgs sector can make the electroweak transition first order, abrupt and violent, proceeding through the nucleation and expansion of bubbles of broken electroweak symmetry in a sea of unbroken symmetry. Inside such bubbles, the physics is different from outside. CP violating processes at the bubble walls and the departure from equilibrium provided by the bubble expansion could in principle generate a net baryon number that persists as the bubbles merge and fill all of space. This scenario, electroweak baryogenesis, is attractive because it operates at energy scales that future particle colliders could potentially probe. It makes predictions about the Higgs sector, about the existence of new particles, about the detailed properties of the electroweak transition itself that are in principle testable. Gravitational wave observatories offer another avenue. A violent first-order electroweak phase transition would have produced gravitational waves, and those waves might still be detectable as a stochastic background that future space-based detectors like LISA could observe. But the cooling does not stop at the electroweak scale, and the story of the universe's thermal history is not complete with electroweak baryogenesis. The universe continued cooling. Further transitions occurred, and the deeper question, whether the asymmetry was generated at the electroweak scale or at the much higher energy scales of grand unification, or perhaps through mechanisms involving the early decay of very heavy particles in the conditions shortly after inflation, remains open. What this chapter asks you to carry is the image of cooling itself, a universe losing heat, and in losing heat, losing symmetry. The high-temperature universe was more symmetric. The forces were unified. The particles were massless. The distinctions that define the low-energy universe we inhabit had not yet appeared. As the universe cooled, the symmetry broke, repeatedly, in transitions that reorganized the structure of physics at every scale. Each transition left a trace. The cosmic microwave background is a trace of the last scattering surface, when the universe cooled enough for neutral atoms to form. The abundances of light elements are a trace of nucleosynthesis, when the universe cooled enough for nuclei to form, and somewhere in the transitions of the very early universe, perhaps at the electroweak scale, perhaps higher, the asymmetry between matter and antimatter was generated, frozen in as the universe passed through a transition that could not be undone. The universe that exists now is a low-temperature universe. Most of its symmetries have already been broken. Most of its phase transitions have already happened. What remains is the residue of those transitions, the matter excess, the cosmic background radiation, the particular values of the physical constants, and the very slow cooling that continues as the universe expands, heading toward a future so cold that the phase transitions of the early universe might as well have occurred in a different world entirely. Which, in a sense, they did. Every atom in your body is the descendant of a flaw, not a design flaw, not a flaw in any intentional sense, a flaw in the arithmetic of annihilation, a mismatch in the cancellation that should, by the most natural reading of the earliest physics, have been perfect. Matter and antimatter produced in the first instance of the universe should have been produced in equal quantities. The processes that generate particle-antiparticle pairs from energy are symmetric in the absence of CP violation. The expectation, from a universe starting in a symmetric initial state, is equal numbers on both sides. The expectation is total mutual destruction. The expectation is a universe of pure radiation, of light without matter, of energy without structure. The expectation was wrong by 1 part in 10 billion, and this chapter refuses to soften that. There is a long tradition in science communication of framing the matter-antimatter asymmetry as a kind of gift as the lucky break, the fortunate imperfection, the cosmological good fortune that allowed stars and planets and life to arise. This framing is not incorrect, but it asks you to receive the information through a lens of comfort that the information itself doesn't carry. The fact is stranger and more neutral than that. The matter you are made of did not survive because the universe was generous. It survived because the arithmetic was fractionally off. Because the rules governing how matter and antimatter interact are not quite symmetric. Because the universe, at the deepest level anyone has yet probed, is slightly, very slightly, by 1 part in 10 billion, broken. Broken is itself a frame. The asymmetry could also be called a feature, a property, a measured quantity, the baryon to photon ratio. The universe is what it is, and the asymmetry is part of what it is. There is no external standard against which to call it flawed. But there is something important in holding the word flaw anyway for a moment before releasing it. Because the matter-antimatter asymmetry is not a gentle imperfection in an otherwise ideal system. It is a fundamental departure from what the simplest, most natural version of the laws of physics would produce. It requires in any successful theory, the existence of processes that violate exact symmetries, charge conjugation, parity, perhaps baryon number itself. These violations are not small adjustments to a basically symmetric framework. They are in each case a fundamental asymmetry built into the laws that govern reality. The universe is not neutral. Everything you have ever touched was produced by that non-neutrality. This chapter is short because the point is complete. There is a particle that passes through you right now, not occasionally, continuously. At this moment, approximately 65 billion solar neutrinos pass through every square centimetre of your body every second. They do not slow down, they do not deflect, they interact with the matter of your body so rarely that the interaction rate is effectively zero. In your entire lifetime, the odds that a solar neutrino will interact with any atom in your body is small enough to be practically negligible. The neutrinos pass through you the way light passes through glass, except more so. Glass at least slows light down and occasionally reflects some of it. You are less than glass to a neutrino, and yet the neutrino may be the particle that explains why you exist. The neutrino is one of the most abundant particles in the universe. For every proton and neutron in the observable universe, there are approximately 1 billion relic neutrinos, neutrinos produced in the early universe that have been travelling ever since, cooling as space expands, now so cold and so slow that they are nearly impossible to detect. They fill space, they permeate everything, and their properties, especially one property in particular, which has been the subject of intense theoretical and experimental work for decades, may encode the answer to the matter-antimatter asymmetry. The property in question is whether the neutrino is a Dirac fermion or a Majorana fermion. This distinction requires a moment of care. All known matter particles are Dirac fermions. A Dirac fermion is a particle that is genuinely different from its antiparticle. The electron and the positron are different particles, different charge, different interactions, distinguishable in every situation where they appear. For a Dirac fermion, the particle and antiparticle are distinct objects. The neutrino, if it is a Dirac particle, has an antineutrino that is distinct from it, a genuine antiparticle, different in some property that, while not charge, since neutrinos are electrically neutral, manifest in how the particle behaves. A Majorana fermion, by contrast, is its own antiparticle. This is possible for neutral particles, since there is no charge that would distinguish them from their antiparticles. For a Majorana neutrino, the neutrino and the antineutrino are the same particle in two different helicity states, one spinning one way relative to its direction of motion, the other spinning the other way. There is no deep distinction between them. The neutrino is self-conjugate. Why does this matter for baryogenesis? Because if neutrinos are Majorana particles, a mechanism called leptogenesis becomes possible. Leptogenesis begins not with baryons but with leptons, with electrons, muons, taus, and neutrinos, the particles not made of quarks. In leptogenesis, very heavy right-handed neutrinos, particles predicted by some extensions of the Standard Model but not yet observed, were produced in the early universe and subsequently decayed. If those decays violated CP symmetry, they would have produced an asymmetry between leptons and antileptons, more leptons than antileptons. Here the sphaleron processes mentioned in Chapter 5 enter again. Sphalerons, the non-perturbative electroweak processes that violate baryon number, also violate lepton number, and they do so in a correlated way that preserves the combination B-L, baryon number minus lepton number. This means that a lepton asymmetry generated by the decay of heavy right-handed neutrinos can be partially converted into a baryon asymmetry by sphaleron processes operating in the hot early universe. The result is baryogenesis through leptogenesis, the matter excess in the baryon sector generated not by a direct baryon number violating process, but by the conversion of a pre-existing lepton asymmetry. The mechanism is indirect, elegant, and disturbingly hard to test experimentally. The key experimental signature of Majorana neutrinos is a process called neutrinoless double beta decay. In ordinary double beta decay, a nucleus simultaneously undergoes two beta decays, emitting two electrons and two antineutrinos. In neutrinoless double beta decay, the two antineutrinos are absent. They annihilate internally because, being Majorana particles, they are their own antiparticles and can cancel each other without any external emission. The signature is two electrons emitted with a combined energy equal to the full decay energy, with no missing energy carried away by neutrinos. This process has never been observed. Experiments searching for it are some of the most sensitive ever built. They use isotopes that undergo ordinary double beta decay, germanium-76, xenon-136, tellurium-130, among others, and instrument them with detectors of extraordinary energy resolution, looking for the sharp peak in the electron energy spectrum that would signal neutrinoless double beta decay. The experiments are underground, shielded from cosmic rays. The isotopes are purified to levels of impurity measured in parts per trillion. The background event rates are reduced to levels measured in events per ton of detector per year. Still nothing. The current experimental limits on the neutrinoless double beta decay rate constrain the effective Majorana neutrino mass, the parameter that would govern the rate if the neutrino is a Majorana particle, to below a fraction of an electron volt. This doesn't exclude Majorana neutrinos. The predicted rate depends on the neutrino mass spectrum and mixing parameters, and for certain mass hierarchies the predicted signal could be below current experimental sensitivity. The next generation of experiments, Nexo, Legend 1000 and others, will push the sensitivity substantially further. The search for Majorana neutrinos is, in essence, a search for a particle that refuses to distinguish itself from its own opposite. A particle for which the question, "Are you matter or antimatter?" has no answer. A particle for which the distinction that shapes everything else in the universe simply doesn't apply. If the neutrino is such a particle, then the deepest explanation for why matter dominates the universe may pass through the strange fact that the particle most abundant in the universe is itself a particle for which the matter-antimatter distinction is undefined. There is something almost recursive about this. The particle that doesn't care about the difference between matter and antimatter may be the particle most responsible for there being a difference between matter and antimatter. The universe keeps its answers near its most paradoxical facts. At some point in the argument, the mechanism of baryogenesis may have to be sought not in the physics of particles at all, but in the physics of the universe at its largest possible scales. In the behavior of fields during inflation, in conditions so early and so extreme that the ordinary categories of particle physics barely apply. This chapter is about that possibility, and about what it feels like to follow an explanation to a place where explanation itself starts to look different. Inflation is the period of extraordinarily rapid exponential expansion that cosmologists believe occurred in the first tiny fraction of a second after the Big Bang, possibly as early as 10 to the power of minus 36 seconds after the beginning, in an epoch so remote that the energy scales involved dwarf anything accessible to experiment by many orders of magnitude. During inflation, the universe expanded faster than light, not violating relativity, since it was space itself expanding rather than anything moving through space, and in doing so it smoothed out inhomogeneities, drove the geometry of the universe close to flatness, and stretched quantum fluctuations to macroscopic scales where they seeded the large-scale structure of the universe we observe. Inflation ended when the inflaton field, the field whose energy drove the rapid expansion, decayed, converting its energy into the hot thermal plasma of the conventional Big Bang. This process is called reheating, and in the dynamics of reheating and of the inflaton field's behavior during and immediately after inflation, there are possible mechanisms for generating the baryon asymmetry. These mechanisms are collectively called baryogenesis during inflation, or, when they involve the direct coupling of the inflaton to baryon number violating operators, inflationary baryogenesis. They differ from electroweak baryogenesis and leptogenesis, not just in their details but in their qualitative character. At the electroweak scale or the scale of heavy right-handed neutrinos, the physics is at least adjacent to what particle physics experiments can probe. At inflationary energy scales, possibly 10 to the 14th or 10 to the 15th giga-electron volts, compared to the TV scales of current colliders, no direct experimental test is possible in any foreseeable technology. One class of inflationary baryogenesis mechanism exploits the departure from thermal equilibrium that inflation itself provides. During and after inflation, the universe is emphatically not in equilibrium. The inflaton is oscillating and decaying. The temperature is varying rapidly. The conditions are nothing like the smooth thermal plasma of equilibrium cosmology. In this environment, CP violating interactions in the inflaton sector, or in the coupling between the inflaton and other fields, can imprint a net baryon number that survives reheating. Another class of mechanism involves the gravitational coupling of the inflaton to the standard model fields. Gravity couples to everything, and the inflationary gravitational background is not CP symmetric. The rapid expansion of space breaks the time reversal symmetry of the dynamics in a way that can, in principle, generate asymmetric production of baryons and antibaryons. These gravitational baryogenesis mechanisms are intriguing because they require only gravitational couplings, interactions that are guaranteed to exist, rather than new physics in the particle sector. But they typically require additional ingredients, such as specific couplings between the Ricci scalar and the baryon current that go beyond the minimal standard model. What all of these mechanisms share is a certain inaccessibility. They operate before any relic of the early universe that we can currently observe was formed. The cosmic microwave background, our deepest direct observational probe of the early universe, was generated 380,000 years after the Big Bang, cosmological epochs after inflation and baryogenesis. The light element abundances that allow us to probe nucleosynthesis take us to roughly 3 minutes after the Big Bang. Beyond that, the universe was opaque to photons. The only probes of earlier times are gravitational waves, neutrinos, and the baryon asymmetry itself. This last point is worth pausing on. The baryon asymmetry, the ratio of baryons to photons, currently measured to be approximately 6 times 10 to the power of -10, is itself an observational probe of baryogenesis. Whatever mechanism generated, it must produce exactly this ratio. This is a constraint. It is not a very tight constraint in terms of discriminating between mechanisms, because many different mechanisms can, in principle, be tuned to produce the right ratio. But it is a constraint, and it connects the inflationary epoch directly to observations made today. There is also the possibility, deeply theoretical, not yet testable, but conceptually important, that the baryon asymmetry is not a consequence of any single mechanism, but emerges from the initial conditions of inflation itself. Some models of eternal inflation and the multiverse suggest that the physical constants and even some of the conserved quantities of our universe are determined not by local physics, but by a selection among many possible universes, a landscape of possibilities from which the observed universe emerges with the specific asymmetry it has not because of a dynamical process, but because of the conditions that prevailed at the beginning of our particular inflationary bubble. This explanation, if it deserves that name, removes the question from the domain of predictive physics almost entirely. It replaces, why does our universe have this baryon asymmetry, with, we observe this baryon asymmetry because universes without it either don't produce observers or produce far fewer. It is the anthropic principle applied to baryogenesis, and it is either a genuine insight about the limitations of physics or an abandonment of the explanatory project, depending on who you ask. This chapter doesn't adjudicate that question. It notes that the river of explanation has reached a place where the banks are gone. The mechanisms traced from the Chiron experiments of the 1960s, through Sakharov's conditions, through electroweak baryogenesis and leptogenesis, lead eventually to territory where the explanatory tools of physics become strained. Not because the questions are unanswerable in principle, physicists continue to work on them with confidence, but because the answers, whatever they are, operate at scales so far from any instrument we possess that the normal feedback loop between theory and experiment becomes very thin, very slow, and very uncertain. The river continues. It just can't be followed all the way to its source. Right now, at this moment as you finish, every baryon in the observable universe is moving in the same direction it has always moved, according to the same laws that produced it, governed by an asymmetry that originated before any of the matter it governs existed in its current form. The universe has not paused, it has not reversed, it has not shown any sign, in all of the time it has been observable, of tending toward the symmetry it departed from in its first moments. There is nothing to resolve. That is not a failure of this account. It is the correct condition for a question that remains genuinely open. The mechanism of baryogenesis has not been identified. The experiments searching for proton decay have not found it. The experiments searching for neutrino-less double beta decay have not found it. The extensions of the standard model that predict the additional CP violation required for any successful baryogenesis mechanism have not been confirmed. The next generation of particle colliders, the next generation of gravitational wave observatories, the next generation of underground detectors, they may find something, they may not. The sensation at the end of this is the same sensation that was present at the beginning. Not stillness, not resolution, motion. The persistent, quiet, unexplained, one-directional motion of everything. But one number sits here at the end, without commentary, without the architecture of explanation around it. For every 1 billion antiprotons produced in the first second of the universe's existence, there were 1,000,000,001 protons. 1. That one proton did not annihilate. It remained. It cooled with the universe. Its quark constituents eventually bound into the stable configuration we know. It participated in nucleosynthesis. It became part of an atom. That atom and its 10 billion to 1 favoured neighbours became gas, became gravity, became a star, became the heavier elements forged in stellar interiors, became a planet, became the chemistry of water and carbon, became the long and branching history of everything that has ever been built from baryonic matter, all of it from an excess of 1. Go back to the first chapter now if you want. The sensation is the same. Everything moving, nothing still, a current without a visible source. But the current has a different weight to it now. You know what the weight is made of. You know approximately how small it is. You know that it remains, after decades of the most sophisticated experimental and theoretical physics ever performed, almost entirely unexplained. The universe is still flowing in one direction. We don't know why.